You can model anything. And if you start carrying that thought to think of all the suppliers, everybody will be working together, it's a whole new paradigm, and it's just starting.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about designing energy systems virtually. You may have flown across the ocean in a Boeing 777. It was the first commercial airliner designed with computers and set the stage for the tool to be used in defense, automotive, and now storage systems. My guest has developed the software for these applications. Their CATIA software is currently used to design about 70% of the vehicles on the road today. It dominates the electric vehicle market, where mechanical and electrical systems are intertwined unlike ever before. But he says the key to their latest innovation is their collaborative capability through what they call a virtual twin. Engineers across the project can adjust and see the repercussions in real time. In the past, especially when it came to battery design, he says the process required a lot of guessing, building, testing, and repeating. These days, most of the existing data is now at the designer's fingertips. They can virtually simulate a battery on a molecular level. The more data you feed in, the closer you get to machine learning, where the software can begin to optimize the design. It's not quite artificial intelligence, but it's clear that from everything from batteries to EVs, this collaborative virtual workspace is now design-driven. My guest today is Rick Sturgeon, Senior Director for Transportation and Mobility for Dassault Systems, a French software company and the global leader in 3D product design and simulation. The Boeing 777 was designed with CATIA in the early 90s, and most recently, their metadata software was used to conduct 70% of the COVID vaccine trials. Dassault has also reworked another medical software called BioVia for the automotive and energy storage sector to help optimize battery design on the molecular level. Right now, they are mainly focused on the automotive industry, but this is EnergyCast after all, and I wanted to explore how this might help perfect large-scale battery storage, particularly in cases where modules are prematurely aging. We also discussed the software's potential for fuel cells as well. Got to have options when it comes for what you drive, right? I hope you enjoy my conversation with Rick Sturgeon. We're here with Rick Sturgeon, Senior Director of Transportation and Mobility for Dassault Systems. And Rick, it would seem that batteries and other systems are always designed on computers. How is this different?
In the old days, what I really noticed in battery, so much of it was build it, test it, see what happened, and do it again. Sometimes with as many as 3 to 6 month lags between actually building something, and it took years. And generally, you ran out of money and you stopped. So batteries didn't move much for a long time. Now, in the last 3-4 years, the concept of computer simulations, especially at the atomic level and building up through that, has really come forth. One of our technologies at Dassault Systems, which we actually took from the drug industry, was a company that would go and put atoms together and then use analytics to figure out what the molecule might do as far as curing a disease. Well, we repurposed that for batteries. In the old ways, you would sit and say, well, let's mix this together and this separator and this anode and this cathode. Let's try it. And we think that'll be good. Now you can actually run hundreds of thousands of scenarios, and it's still not perfect. You have to pick the best 5 or 6 and build those and continue iterating. And the whole industry is in that mode, and we're very involved.
You got a lot of wheels turning in my head about this. So how much of this is a proprietary software? You said you brought it in from the pharmaceutical, right?
Yes.
Yeah. So how much of this software is new that you guys developed?
It was all BioVia was the name of the company we purchased, and adding it to our cloud platform, the same platform you could develop a Boeing 787 on or an Airbus. And to put it in perspective of the scale we have with our CATIA product, I think around 70% of all automobiles manufactured were created with it, and 85% of all EVs, because EVs have really jumped onto this concept of an integrated platform, now moving to virtual twins. But within that, it still comes down to having all the data data available, but the capability of the simulations. And there's thousands of different simulations. But to develop a battery, you have to look at heat, you have to look at swelling, you have to look at flammability. But at the most basic level, you're looking for improvements in energy density.
You described doing thousands of simulations on this. So it has me wondering, is it almost like artificial intelligence? Can there be inputs to ask the computer to come up with the most optimal solution?
Well, if you look at Star Trek and, you say computer and it always is right, we're not there. You have to set them up, the framework that you want to do, the simulations you want to run, many concurrently. We call them trade studies, but that can be looking clear from the molecular dynamics. There is AI absolutely used in it. But if you think what artificial intelligence really is, it's primarily machine learning. And what that means is if it seems something enough and been trained, then it'll move you in that direction. Generally, when you're looking at the cell level, you're trying to find something new that's better than anything before. You have to collect and have easily available all kinds of analytics. We connect into some of those and try to use all the latest research. But really, to use big analytics, you have to get the data all connected. And that's the strength of our 3D Experience cloud platform, because in there's one part number, there's just one of everything. And this is something we did for the aerospace industry. When you pull out data about something, you have everything that's affected and it's ready to go. Now, in the older approach, you had thousands of files and almost none of the time running the analysis. This platform was used to conduct 70% of the COVID trials globally, artificial intelligence building on data. So we try to pull from all different industries, aerospace, industrial, et cetera, and put it all in the same place and share the knowledge across. It's really an exponential change in capabilities, all moving to the perfect virtual twin like Star Trek. We're on the journey.
Yeah, absolutely. Okay, so what is a virtual twin?
You've probably heard of the digital twin, but digital twin really means you just find a way to connect all the data, even though it's not aligned. The virtual twin is when all the data sits on one platform, all the applications work together on that same data set rather than being spread in little silos all over the place. And then what it has the ability to do across the whole framework, a thing called model-based systems engineering, a language called SysML, and we have the primary tool for that. It used to be called No Magic. We now call it CATIA Magic. It's called Cameo. Well, pretty much the majority of the defense and aerospace industry uses it, and it's now heavily moved into automotive for electronics, but we've seen it also move heavily into advanced battery development, because there you can simulate all the requirements, align them, do some of your trade-offs before you ever start making things. Well, then with the virtual twin, that's part of it. But then as you move on and you start doing this simulation, you start coming up with some of the formulations, you can actually start building a cell level of battery and then go through automatically and see how you're going to put the battery together, how you're going to package it in the car. And we haven't talked about the effect that the electric motor has. They didn't use a whole bunch of chemical and electrical, but now that's the thing, right? And I always thought you could just buy a motor off the shelf, an electric motor, and put it in there. Well, they're so inefficient, they're so heavy, and many of the big OEMs are developing their own electric motors, custom designed in many cases for each vehicle. Well, we can simulate that development, including the noise of the fluid bouncing around in the electric motor. The electric motor is silent. It's actually a big issue. You can hear the fluid bouncing around inside the gears. So we even have simulation that optimizes that while you're putting together how the gears will go and how the electric EMF currents will flow. The reason I go into that, the virtual twin means everything, even clear through how it's going to be used in service, how it's going to be manufactured, that can all be created as it's being created, really. All the simulations kick in. So the virtual twin, in my mind, it's like the old drawing, the engineer doing 2D drafting on a board. But that's how, until the 777, every plane was developed. Then we went to this concept of all these systems. And CATIA is a good example of where you actually can see things as you develop them. The virtual twin is bringing it back to how engineers work. As one person in India changes something on an assembly, everybody in the world sees how that's affected. It's almost like we're in the same room working on the same thing, but the manufacturing's being affected. It's visible. Everything's being affected at once. It's a massive change. And the EV companies, which are the mass majority, Tesla, NIO, Rivian, on, are using our tool. It's a massive multi-times cost improvement and speed.
You mentioned the 777, and I wanted to get into that. You know, when I was in business school, we all learned that case study, what happened with the 777. It was the first commercial airliner designed with computers, right? It was designed with, I think, AutoCAD or something. And
it was called CATIA.
It was CATIA. Okay.
Yes.
And so the case study that came out with that was, yeah, it was great. It was designed in a computer, but then it was like they didn't make the considerations for where the mechanic goes. Right? Was that it? And so take us through from the early days of the 777 and all the lessons learned from that. How is the software smart enough to take into consideration that there will be a real life counterpart to this with real people possibly wrenching on things?
Well, you like stories. About 2 or 3 years ago, we took Alan Mulally, if you've heard that name, into the Automotive Hall of Fame because he had gone to Ford and probably you could argue turned around Ford from a product perspective. When we were bringing him in, this is a small group of people, the automotive leadership really of the U.S., actually the world. He needed 2 people to speak for him. And he asked Bill Ford to do it. And he asked our chairman, Bernard Charles, and they told this story. When Mulally was the chief engineer, whatever they called it, of the 777, Bernard goes to see him. And our company had been using computers in France at some level on the Dassault aerospace products. And this company is spun out. When he walked in, Mulally said, I know everything about designing an airplane. And Bernard said, I know everything about designing an airplane with a computer. And their careers locked. Right. And so I'm sure that there were the issues that you talked about early on. But now if we go to where we are today, and I mentioned some of this earlier, the concept of MBSE was really developed by NASA and then the Air Force. And in that model, you certainly model what the product's going to do, but you also model what all the users of that product are going to do. What's going to happen in the environment, how you're going to manufacture it. You create in the requirements model, and it is a working model, how everything's going to be affected. And then you try it and you change stuff and you optimize. I took a bunch of MIT courses to make sure that I knew enough to talk to you about this. And MIT would say that you spend an extra 20% early in the program as compared to what you normally would, but you reduce half the cost of the program by getting it right up front and getting everybody working on the more detailed level. Now, we also, in this virtual twin, it's not all just these requirements. It actually can start doing some of the simulations, and some of it at deep research, some of it more at development level. For example, what we were talking about earlier, that concept of starting to optimize what the chemistry needs to be, what the sizing of the battery should be, where its separators are, anodes, cathodes, and then how to package that, and then how to package that completed cell in the vehicle, and then how to get the motor right, and then ultimately making sure, as you pointed out, the analogy used with Boeing, making sure there's room to do service. And we actually often show examples. At CES, the computer show, we can make it so you can put the goggles in and walk around inside. There in real time, it would change. I think we also, from an EV perspective, go from the normal HVAC from an energy perspective, where you just blow air into the car, right? Right there in the simulation, you could say, well, I want to change that out. I want to put in radiant heat around each passenger. And that took like 40%, maybe 50% of the load out of the vehicle. And it also made the heating better. But that wasn't something you built. You could literally make those changes in and changes out. We were doing it on the floor at CES up on the cloud. And if you start carrying that thought to think of all the suppliers, everybody will be working together, changing, innovating, adjusting, obviously seeing what's effects it's going to have on other people. It's a whole new paradigm, and it's just starting.
Yeah. And Rick, it sounds to me like you definitely are able to do this faster. All the setup, all that time's gone. But just in what you've seen so far, what are some of the challenges you've been able to overcome with this modeling system specifically? What have been some nice surprises?
When we first took these technologies, this concept of everybody working on the cloud, or at least this 3D experience platform, in our cloud platform, you can have multiple people working on the same CAD models concurrently. Maybe you were attached to something, your part, and some other guy just changed that part. That's immediate communication. What you were trying to do is affected by somebody else. It's almost like they were in a big room. We see now many companies using this platform to try to coordinate everybody globally across the whole program program in more of a semi-real-time team as compared to have these long, you do this piece of work, hand it back in, we'll see if it works, iterations.
I just spent some time working in large scale storage, lithium ion, tens of megawatts at a time. And the thing that I can report is that these modules are degrading quickly. We're talking about EVs. That seems to be what this software and definitely what you're focused on. But I'm curious how this might extend beyond EVs, particularly with large scale energy storage. So storage is storage, right? Batteries are batteries. Any talk about that?
I don't necessarily work on that myself, but I was a power engineer doing power plants when I first started out. And you mentioned the degradation of the lithium ion was a problem. I have to be careful how I lay this out because I'm aware of some things. But any lithium ion manufacturing facility, which we're engaged in several, they go and they fully charge each cell and then they fully discharge it. If it charges exactly at the same wave curve as it went up and it comes down exactly the same, that's ideal. It never happens that way. It'll come down in a different curve. And what's in between is called hysteresis, and that's really heat. But that also is a signature, it turns out, because what they also do is they'll charge and discharge things 20, 30, 50 times and really get some variables or some things that they can tie to that battery, like a signature. And then they'll age those batteries. And it turns out these cells age very differently. In other words, fail. And the way they fail is they start building these little tentacles, really. And ultimately, those start interfering and over a long period called failure. Well, those build at a very different level depending on the battery, even on the same manufacturing line on the same cell. It's like baking cakes. Every cake that comes out, occasionally there's a miss, right? What they started doing, if you take those cells and turn them into a battery, if just a few cells start failing, it starts to go. So aging is really driven by the weakest cells in the battery, and they might have thousands, right? What they're trying to do now, or at least the research is showing, they can actually start sorting those at the manufacturing site and put them together so that the cells will degrade in a common manner. And that has a huge effect in aggregate. Now, you get into the issue of power storage versus an auto. Autos are pushing for 100,000 miles and so forth. I think there's a time factor involved in this too. And with a power plant, they want to last 10, 15, 20 years, right? You have to change the batteries occasionally.
So you're saying they're able to find ways to keep the batteries from prematurely aging. Would your software be able to help with something like that, especially on these big systems where you have hundreds, if not thousands of lithium modules in one place?
Well, yeah, we start simulating at the very deep molecular level. And we do a thing like chemistry to pack performance. And that does include aging and durability as well as performance. What affects a battery? It's how much energy do you pull out of it? What's the load when you do it? And how often? The load has to be strategically designed to keep its life.
Do you think that there's opportunities to model power systems beyond lithium ion batteries, like fuel cells or non-lithium chemical batteries? I mean, software is software, right?
You can model anything, and you certainly can model, and we are modeling fuel cells. I actually worked at a company called Allied Signal, which is later called Honeywell. We did all the fuel cells for space for the NASA program in the 60s. We actually were selected when Chrysler 20 years ago was working with the Department of Energy to try to build a fuel cell vehicle. There's a thing called the PEM membrane. It's this membrane that ions will go through. You have to have some platinum to help catalyst, and I'm sure there's 100 things going on, but people have been working on that for 25 years. They used to be huge. Now they're becoming smaller, more precise, and the same simulations, the same capabilities for material simulations, for chemical simulations. We're doing all that on those, and the advanced analytics and the advanced simulations are moving all of that forward. And you have this other question of the power grid. You get into the next thing of the smart city. Now, you think of the smart city as EVs running around in them and mobility apps and so forth connecting. And we actually were two of the layers, I believe, in the smart city of Singapore like 10 years ago. And that's probably the most advanced one. In all of those, there's certainly how will the city reconfigure itself, but there's also that component of how will the communications of all this handle, and then how will the power flow? Because the power flow, I mean, we have Ford's Lightning. Ford really, one of their big marketing things was you could use the battery to power your house for 3 days, right? But it brings brings back the question of how will the utilities use that to help their grids when they're in trouble? Stability in the grid, storage, et cetera. And I think that's a whole new space.
I mentioned fuel cells, I think more in large scale storage, but you mentioned you were working on fuel cells too. So one of the things I talk about as well with EVs is I kind of believe that there's a big potential for electric vehicles to be fuel cell. I sometimes think that maybe we might look at EVs, this idea that 100% are going to be battery EVs. I think that we're going to move on to fuel cells. And so I would have to think that that's something you're also considering too, this idea that we're modeling for EVs, but we probably also need to be modeling for those vehicles as well, right?
Well, various customers and various automotive companies have different strategies. And I think we have one customer in Europe is only doing hydrogen-powered vehicles. They're building all of the scenarios, pure EVs, plug-in hybrids, start-stop, all of them. And they're going to let the market decide and just be prepared to drive with it. I think one of the challenges for hydrogen, and we're seeing it also with plug-in EVs, is to have a place to recharge them. And hydrogen is a whole nother concern. How would you, in a large scale, do that for the vehicles you and I might drive? That infrastructure isn't there.
Yeah, look, it's an infrastructure challenge no matter which one you choose, right? I think one of the benefits of possibly doing hydrogen is you could still be using all the gas stations and people could just fill up there. And I think that's something that a lot of folks are familiar with. There's also the considerations of you got to upgrade the grid. If all of this charging, all of this extra electrical consumption is be having distribution level in neighborhoods.
We seem to run in some regions of the country, the coast, for example, the grid pretty close to maximum some parts of the year. And if we lose a plant, sometimes we get blackouts. The energy department, we had a leadership convention and the guy supposed to be working on this was there. And he said, we've analyzed it and we figured out that the grid can support it. He didn't look that confident, but that's what he said. and all the automotive leaders were there. Well, I was sitting there from my power background and thinking, yeah, but what if you do get a blackout? I'm going to just charge my house for the next 3 days off of my vehicle. When the grid comes back on, it's going to get a massive spike in demand, way beyond what the demand was when it went down. Will they really be able to bring the grid back up? Or will they have to go with rolling blackouts for a while? It's sort of something that's been in the back of my mind as a use case. I just hope that that's been looked at by your audience.
I hope so too. So finally, Dassault, this technology, you said it's being used by Rivian and a few other clients and everything. Where do you see this ultimately going? And what do you see as maybe the next steps there? Because optimizing EV fleets and microgrids, it really sounds like a pretty daunting task. So where do you think this is all going, Rick?
Our big focus now is sustainability, CO2 reduction. How can we make sure that every screw you put on a vehicle has minimized the CO2 footprint and where the material comes from, how it's used, how it's manufactured? The virtual twin of everything is the goal. And within that twin, it's to harmonize product, nature, and life. And we're all working toward it.
Well said. All right. Rick Sturgeon, Dassault Systems, thank you so much for your time.
Thank you. This was fun. I love to talk about energy.
So do I, obviously. That was Rick Sturgeon, Senior Director for Transportation and Mobility for Dassault Systems, a leader in automotive software design. I want to thank Rick for his time. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the wrong completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 144. Be sure to join us next week. We learn why Europe is turning again towards coal. Until then, I'm Jay Downhauer. We'll see you next time.